All right. So thanks everyone for coming. Big crowd to talk about Pig and data science. So it's great to see so many people interested in this. All right, so what are we going to talk about? So first I'm going to introduce myself and give a little bit of preliminaries about Pig. Then we're going to kind of talk about where Pig fits in the data science tool bag. All right. And then we're going to go through some examples with a particular emphasis on unstructured data analysis. And then I'll take some questions. And just for reference, there's actually a bibliography. So don't be scared that you're going to a talk with a bibliography. It happens. All right, so who am I? My name's Casey Stella, and I work as, so you can tell by the shirt, I work at Hortonworks. I'm a principal architect. So I have sort of 1 foot inside of architecture and 1 foot inside of data science. Before this, I was doing data mining in clinical informatics from a startup that was spun out of the Cleveland Clinic in Cleveland. So I'm based out of Cleveland. So I'm not a Valley native or anything like that. And before that, I was doing signal processing. So we created our own MapReduce-based framework in the oil industry. And we use that. So that's kind of where I got the notion that it might be an interesting thing to do large-scale data processing. And before that, I was a graduate student and very poor. All right, so I'm going to talk about Pig. So Pig, normally when people think about Pig, they think, well, it's an ETL tool. It's a scripting language on Hadoop. And the second thought is, well, it's an ETL tool. It's going to help me transform my data that I've pulled into Hadoop. I think that Pig is much more than that. And hopefully, at the end of the talk, you'll come away with at least some notion that Pig actually has a lot of nice things that will lend itself to a broader variety of transformations, I guess. Maybe it is still ETL, but part of that T is data science. Okay, so what does it do? It is a high-level abstraction which transforms operations with a full set of relational operations into into MapReduce as of legacy Hadoop and or TES jobs now. Right? It optimizes it such that the minimum number of jobs, best effort, get run. So that's very nice. You can work at a nice abstraction. And you have all the familiar relational primitives, so inner joins, left joins, Cartesian products if you're so bold and brave. But the nice thing about it is, it's the same thing applies to Hive and the other scripting languages. It's very extensible by user-defined functions. So we're going to talk a little bit more about that, and we're going to talk about how this has been used to really build a robust capability of doing data science inside of Pig. Okay, so what does Pig look like? And the reason why I'm including this slide, a lot of people know Pig, and a lot of people have seen the word count example. But the reason why I do this is because I have a pet peeve. Every time that I see a Pig word count example, the relations are named A, B, C, and D. Please do not name your relations A, B, C. Every time I get a bully pulpit, I'm just going to harp on that. It's not about the talk. Just stop naming your relations A, B, C, and D. It's not a good thing. Okay. All right, so we load data into sentences that has some structure, right? We can tokenize the sentences into words, flatten that out, and then we can group the words together, right? Then we can essentially iterate over that collection and count for each group, and that'll generate our word count, right? So that's the canonical example, just to kind of give you a flavor of what Pig looks like for those of you who are sort of unfamiliar. Okay, so when I say data science, I actually include some amounts of data engineering, and I know that's kind of heresy, but I have a very broad vision. I have a very broad view of data science, and the reason why is because 80% of my time when I'm doing a data science task is actually doing data cleansing, and I don't treat that as something that's bad. Actually, that data cleansing is very important. Grubbing around in the data gives you a better appreciation for the distribution of the data, and there's data science activities in that grubbing. Understanding the fundamental distribution of how your data is situated and how it changes over time can affect data science, can affect the analytics that come after. Data science does not exist inside of a vacuum. So like any ETL tool, you can imagine Pig can do this kind of grubbing, and it is sort of built in. And that's kind of what gives it the power. So a core prerequisite to analyzing data is just to understand it. So computing distributional statistics on the data, sort of simple statistics. So going back to basics. The other theme of the talk that I want to kind of harp on at the first part of this is that not all of data science is machine learning, and not all of data science started in 1980, right? We've been doing data science since Pascal, right? Statistics exist and can be done and can give insight and can be effective. So we need to broaden this out, and I'm going to kind of start by talking about that. So computing distributional statistics on data and sampling. Sort of that's in the statistician's tool bag. It always has been, or it has been for a very, very long time, right? Sampling is very important. So I'm going to lead into DataFoo. So DataFoo is an incubated project, Apache incubated project, which is a set of UDFs to enhance Pig's utility for data science and information retrieval as well. There's a lot of different things in there, but it's all toward IR and data science, right? So what can you do inside of DataFoo? You can compute quantiles of data. Sort of you have the notion of not just quantiles of data, looking at all the data, but also streaming quantiles that are probabilistic. So we'll give a best guess, and we'll get some performance characteristics, some nice performance characteristics back, right? Sampling. Sort of built into Pig is Bernoulli sampling. You give it a percentage, I'm going to give it back to you, right? But also simple random sample, which with best effort, if I want 1,000 samples rather than some percentage, it will, with best effort, give me back 1,000 samples. It may be 999, it may be 1,001, but it will, with high probability, be very close to that number. And also, if you want to take a performance hit, you can do reservoir sampling, which will give you exactly back the number, right? So these are the simple uniform samples, right? The other thing that it can do is the non-uniform samples, where you get weighted samples. So that's very useful when you're trying to construct. So why is this useful? Well, a lot of data science actually still continues to be done on high memory boxes, where you can't pull all the data in. You need to do complex analysis. And it doesn't fit well within any of the distributed frameworks right now. It doesn't fit well within MapReduce. Maybe Spark isn't, maybe it would be a lot of effort to use Spark. Or maybe you just have some really, really great academic libraries from R or Python. So sampling down is still a very viable alternative, and Pig lets you do that. And you have random sample with replacement. So we'll kind of dig into the random sample with replacement. So random sample with replacement enables something called bootstrapping, which is a resampling method. So if you have some sort of estimator like mean that you want to look at, and you have a sample of data, you can essentially resample that data multiple times and then look at the variance of that estimator across all of the resamples. So you take one sample and you replicate it multiple times. And you do that using this sample with replacement. There's some distributional assumptions there that the samples are independent and identically distributed. But for the most part, it's a very, I mean, I think this has been used since the 19th century, right? To get a notion of what an estimator is. How does your data look? Instead of taking one big sample and saying, here's the average height in the room, I'm going to have multiple samples, and I'm going to look how it changes. If it doesn't change very much, then you know you have a very stable sample, or you have a very stable estimator. Okay. So DataFoo does this via two UDFs. Something to know about DataFoo, they have really long names for their UDFs, and sometimes they're confusing, but it's super useful. So it's broken the sampling with replacement into simple random sample with replacement vote, which takes for each position in the random sample, it votes which of the elements is the most, should be in that spot. And then simple random sample with replacement elect chooses that sample. So you end up with a mechanism to create 100 bootstrap samples very easily inside of Pig. And there are, I mean, I can't do it justice inside of one slide. There are examples, full examples about using this to do using this to use to generate a bootstrap. Okay, so now enough of my spiel about statistics. We'll go into machine learning. Right, so machine learning, it's the study of systems that can learn from data. Right, everyone knows what machine learning is. And generally, it falls into two categories, supervised and unsupervised. So unsupervised are things like clustering. K means clustering. You'll look in the big data world to do this inside of Mahout, now with MLlib, Hexadata, things like that. Right. Outlier detection, so knowing whenever things deviate. So that's still some amount of, you can use statistics to do that. You can also use machine learning. A lot of people have used, sort of to great effect, support vector machine, two-class support vector machines to understand whether or not a given point is inside or outside of sort of what you want to call an inlier versus an outlier. Okay? And market basket analysis. This is the people who buy beer often, or people who buy diapers often also buy beer type of analysis. So Mahout has an implementation of that. Okay, so, and supervised learning, which is what a lot of people think of. So classification, I'm classifying something, some vector into a set of categories. Regression, I'm predicting a value, like logistic regression, that sort of thing. And recommendation, so recommendation engines. I bought these things, what other things should I buy? What other things might I be interested in? Okay, so how does this connect to Pig? So machine learning at scale in Hadoop can fall into two broad categories, in my view. There may be more, but these are the two I want to talk about. So you build one large model on all the data. So you use the power of Hadoop and Mahout or Hexadata or whatever, and you build your classifier on all the data, or 80% of the data, and then you test on the 20%. But you get the gist. You're running the training on Hadoop. Or you sample the large data, and you build a model based on that sample. Or you build multiple models with multiple samples, and you combine them with some, even with weighted averages or whatever, right? So most people think about data science on Hadoop as the first. And I actually I think that Pig really is successful in doing the second, because the training often has to be done not all the time. It's the application that can be scaled. So once you have the model, it's important for scalability to apply the model at scale, not necessarily to train the model at scale. This comes with some underlying assumptions. A sample of the data might not contain rare events. It might not be quite as good. But actually, for a lot of cases, this is a very reasonable thing to do. And the benefit of it is you get to create the sample. You get to build the model out of band on a high memory node using whatever language you want. And then you can apply the model with Pig, if it's a JVM oriented. I think it might be. I think Pig can do Python UDFs now, not just Jython. So also Python, as well as any of the JVM languages, to generate the model and apply it. Right? Okay. So Pig shines at this batch application of applying this model. Right? So this is generally of the form: train the model out of band and write a UDF, or use an existing UDF. So one of the examples of an existing UDF that uses the model is some of the NLP work. So Datafoo has some of the open NLP models built into UDF. So if you want to do sentence segmentation, part-of-speech tagging, that sort of thing, those are using models built out of band. And you call the UDF from the Pig script. And so what I wanted to do here, and I can't show all the code, but I want to show some code about sort of a fully working example in the domain of natural language processing. So what's natural language processing? It's the intersection of computer science, linguistics, and math. And it covers the understanding. So the idea is understanding what you mean rather than what the text is. Right? So this is very broad. Historically, it was in the purview of linguists. It then moved to being more interested in computer scientists, and then it became even more interesting once statistical machine learning came about, and they realized that you can actually do a lot of this stuff with much higher accuracy using statistical models. And now with sort of everyone talking about deep learning, there's sort of a movement to rethink a lot of these things in terms of deep learning. So being that you have you can build more complex input, and you can eke out more performance. But the idea is that computer scientists are now interested, statisticians are interested in this. And it also happens to be that industry is interested in it, because industry has, a lot of people have been dropping their free text because they don't know how to analyze it. The best they could do before is run regular expressions over it, which may be effective, but isn't a complete solution. Okay, so it happens to be that, and I'm not exactly sure why, there's a lot of academic natural language processing libraries ignoring OpenNLP. There are a number of academic machine learning oriented NLP libraries in Java on the JVM. So it makes it a uniquely interesting place to fit within Pig. So there's OpenNLP, which is the Apache project. You'll go to that if you want to find your basic part-of-speech tag, maximum entropy, a sentence segmentation type thing. Stanford Core NLP has some really cutting-edge stuff. It's not Apache licensed, but it has some really cutting-edge stuff. It expands, in addition to the tokenization, sentence segmentation type basic stuff that you have, it expands to includes some sentiment analysis, right? And that's what we'll kind of focus in on in the next section. And Mallet, which is a topic modeling library that came out of UMass Amherst, which I'm particularly fond of because I think it's quite good. And actually, Stanford Core NLP also has topic modeling built in. So this is generally low volume, complex analysis, which is often the case inside of doing data science on unstructured data. Big companies often don't have a ton of it, or if they do have a ton of it, it's on tape that they need to sort of dredge up. But it's easy to convince them if they can gain value that they should start including it. There are some exceptions to this. The medical industry has been keeping this stuff around for some time, so that's good. So you often see, sometimes it's high volume, complex analysis as well, with search engines, obviously, not to cast aspersions at the difficulty of creating a search engine. This is high volume and complex, as well as social media content analysis. So you'll see a lot of work on sentiment analysis inside of Twitter, stuff like that, or from data from Twitter. So it fits within the many small data problems in parallel that fits well within the assumptions to scale this inside of Pig. So you build the models out of band, you can now scale it using Pig or MapReduce or whatever, but we'll talk about Pig. And it's ideal for encapsulating inside of Pig UDFs. So while I'm not going to run the demo because it takes multiple hours to run, I'll show the code, and you can download the code on my GitHub repository. But so here's the idea. Stanford Core NLP added sentiment analysis, and it's the work of Richard Soker and a broad variety of people. They applied a deep learning model, in particular convolutional neural networks, to predicting sentiment of sentences inside of movie reviews. So this sort of the standard movie review analysis. So there's a really large set of IMDb movie reviews out there that give you it's a labeled data set of the whole review with positive or negative, right? They ran their model on Rotten Tomatoes data. I thought it would be interesting to look and see if their model worked on movie review data from IMDb. The problem is that their model assumed a sentence, whereas the data that I had assumed a whole document. So I thought this wasn't going to be a problem at all. But actually, it turns out to be a relatively complicated thing. If you just average the prediction across all the sentences, that ends up with a really bad result. So if you want to, you can look at the code to see how I solved it. But I had to use a little bit of machine learning, or I had to use a little bit of data science to do that as well. So there's something called Wilson's ratio that was used to aggregate these predictions at the sentence level into a document level prediction to recover the result that we got from the research paper. Okay, so this is what the UDF looks like. It's very simple. I've removed a lot of the cruft, but this is kind of the basic idea. You extend eval func. I'm going to take in a string and I'm going to output a string. The string is my document. The input is my document. The output is the recommendation, right? I'm going to predict it using the model. I've wrapped most of the actual usage of core NLP, but it's not much actually. It's mostly just applying the core NLP model and rolling up the results inside of a sentiment analyzer. So you get the sentiment class and you return it out. Very easy. This is kind of the pattern. And this is the pig script. So I'm going to load the data. I'm going to register my pig, a UDF. I'm going to define it so I can reference it without the fully qualified name. I'm going to load the positive reviews and the negative reviews from the training data that I want to apply the model to. I want to generate the true sentiment as well as the predicted sentiment for the negative examples and the positive examples. And then I want to group them together. I'm sorry, I want to generate the true sentiment for each of them, group them together, and then apply on that union. I want to predict the sentiment using my UDF. So sentiment analysis, parenthesis document. Okay? And then I want to store the predictions. And then there's a second pig UDF. There's actually a second pig script to compute how well I did. So as is standard for looking at results of this kind, I generated a confusion matrix. So it turns out that the core NLP library has a couple of issues. It's extremely memory intensive, and it's actually also extremely CPU intensive. So it takes a long time to run. So running this on my sandbox, which is sort of the orientation, so you can follow along at home, I sampled the data down into around 1,000. So you'll notice that 1,022, I did the simple Bernoulli sample, so the sample built inside of Pig, and you saw I knew exactly how many I had, and I gave the probability. And you saw it didn't really get me 1,000, it gave me a little bit more than 1,000. That's one of the deficiencies inside of that the Datafoo samples try to correct. Okay, so on a confusion matrix, the rows are what I predicted and the columns are what the actual value was. So what you're going to want to see is along the diagonal, that 367 and 422, that should be high along the diagonal. Off the diagonal are my errors, true positives and true negatives, true positives and false positives, right? Those should be relatively equal and low. That's what you're looking for. And you see it's relatively equal and relatively low. So this actually recovers, 77.2 recovers what we saw in the research paper as well. It was around 76, so within statistical noise. Taking each of the individual predictions by sentence, averaging them, taking the maximum of the last half, all of those resulted in somewhere around 50% to 60%. So the Wilson's ratio actually worked quite well at recovering the actual prediction of the whole document. So just FYI. All right, so I'll stop. Actually have 16 minutes to answer questions. If anyone has anything. Yep. So the question was, can you use the R language of the UDF? To my knowledge, no, you cannot, because there's not a JVM implementation of R. There is a project on doing a JVM implementation of R called RenGen, but it's not mature enough, I would say. But you can do, for instance, if you build a model, you can do Hadoop streaming or RMR or any of those things. Any other questions? Yep. The question is, how do you compare Pig and Spark? Pig and Spark, in some ways, are doing two quite different things. Pig is, in the current implementation, is around doing batch processing without the in-memory, or when I say in-memory, Spark degrades gracefully if it runs out of memory. without the in-memory component. The comparison is mostly if you're comfortable inside a Pig, if you're comfortable with writing Scala or you're comfortable with writing Java, then that's fine. You can use Spark. Pig is a nice scripting language, and it comes with all the advantages of a scripting language. It's fairly comprehensible, and I haven't seen anyone that didn't pick up Pig within about a day. The language is extremely simple. So I would say Pig is good at a more narrow use case than Spark, but that use case actually has a lot of benefit to data science. Yeah.
You talked about using samplers to build your model out of band, so to speak, so often applying the model. Can you give an example where using a sample is maybe not sufficient, or you would want to build your model with things?
Sure. So the question is, I talked a lot about sampling. When is it insufficient, right? When are you going to get into trouble? So you're going to get into trouble when you have very rare events that you want to include, and you don't know about them a priori, right? So in the medical space, when we were looking at building predictive models at Explorus, we looked at, so we were interested in capturing some actual rare diseases and some of the diagnoses and things like that associated with those rare diseases. So that's one example. The other example is the situation when sampling is actually quite hard, when you have complex data that has a lot of relational interplay. So another example from the medical space, you have diagnoses you want to predict, but each of the diagnoses is associated with a patient, and a patient has a ton of different things associated with them, observations, labs, et cetera, et cetera. That, figuring out how to sample that, you kind of have to sample the whole bundle. Do you sample by patient, is that right, or do you sample by diagnoses? Each have pros and cons, right? If you sample by diagnosis, you have more of a control. You can do a weighted sample to capture those rare events that you want to include in your model that you couldn't necessarily do sampling by patient. But if you sample by patient, you don't have as much control to include those rare events in an easy way. So that's a long-winded answer to your question. Hope it suffices. Any other questions? Great questions so far. All right, well, I finished early. So thanks a lot.